Okay, so on this single page that you have, you're going to be putting 8 boxes, and we're going to put information in each one of those boxes. So right now, your page, you have a blank page. I want you to divide it down the middle, vertically. And then, yeah, you can fold it in half if you want. And then I want you to divide it horizontally. And then you'll have 4 equal sections. And then once you've done that, cut each of those sections in half so that you have 8 equal boxes to put your notes in. Okay, I'm going to erase this lovely drawing. The top box, top right box, you're going to label tree diagrams. We're going to put some notes inside it, so write small enough so that you can put an example. And then on the other side, is going to be counting principle. These are the 2 things we started with on the first day of this unit. We started with tree diagrams and the counting principle. The nice thing about tree diagrams is you can see what all the outcomes are. You actually know the outcomes, like heads, 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 tails, tails, heads, tails, tails. So we can write that down. You can, that's too big. You can see what all the outcomes are. And with the counting principle, you just know the number of outcomes. So the tree diagram is going to let us see what the outcomes are, and the counting principle is going to tell us how many there are. So let's say we're doing a tree diagram for a problem, and we say we flip a coin, and a problem might say it's a fair coin, or it might just say it's a coin. And then we roll a die. Remember that sometimes they call a die a number cube. Sometimes they say it's a fair-sided number cube. They say all kinds of weird things. But essentially, they're all 6-sided cubes with the options 1, 2, 3, 4, 5, and 6. So when we're drawing a tree diagram, the first thing we want to remember is that the only thing that goes into the diagram are the possible outcomes. So flipping the coin, that's an action. So I'm not going to put flip in my tree diagram. What do I get when I flip the coin? Heads or tails. That's what goes in the diagram. So we start out with just kind of a singular dot, and we say we could either get heads or tails when we flip that coin. And then we roll the die second. So the next part of the tree diagram is the die rolling. And when we roll the die, we know we could get a 1, a 2, a 3, a 4, a 5, or a 6. These 2 things are independent of each other. The flipping of the coin doesn't affect what happens when we roll the die. So we can get a 1, a 2, a 3, a 4, a 5, or a 6. And then if we get tails on the first one, we can still get a 1, a 2, a 3, a 4, a 5, or a 6. And then we can, from this diagram, we can count how many outcomes there are. The easiest way to count the number of outcomes is just to count the outside edge of your tree diagram. For example, just going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 12 outcomes. So we can count it that way. What I have been asking you to do is once you make your tree diagram is to list all of the possible outcomes. And so we can do heads and then a 1, heads and then a 2, heads and then a 3, and just keep listing all of the outcomes that you see. Those are all the outcomes of getting heads first, and then all of the outcomes of getting tails first. And then we put those nice curly brackets Okay, those are really just wavy lines. Curly brackets around it. And when we've listed all of them, we call that the sample space. The sample space is all of the possible outcomes that we got. That's called the sample space. Now, when you're looking at the sample space, it makes finding probabilities of things like this really easy. Like if I say, what's the probability of rolling an even number? Well, how many of these outcomes have an even number in them? 6 of them. And how many total outcomes are there? 12. So 6 out of 12, which we would simplify to 1/2. I will tell you on the quizzes today, on one of them, they didn't simplify the fractions. I don't know why they didn't simplify the fractions, but you should always simplify the fractions. Okay, so that's the tree diagram. Counting principle is when we just multiply the different number of outcomes. Yes?
For the tree diagram, do the brackets go on both sides? Or?
They do. There's one on the left and one on the right. Not like the weird piecewise functions where they only put a curly bracket on one side. The counting principle is when we multiplied all the number of options there were, right? So with the counting principle, you want to know how many actions there are. And I say actions, it could be a decision that's getting made. But essentially, how many different things do you have to find? For example, there are some license plate problems, and they'll say the license plate is made up of 3 letters and 3 numbers. Well, if there's 3 letters and 3 numbers, how many decisions would you have to make to choose a license plate? 6. Okay, so let's say that we flip a coin 3 times. So when we flip a coin, we know that we can get heads or tails. There's 2 possible outcomes. So the gut instinct for a lot of people is just to say 3 times 2. But we don't want to do that because 3 is not a number of outcomes. And the only thing we multiply is how many outcomes there are. Okay? So if you look back at the tree diagram, there are 2 outcomes for the coin, 6 outcomes for the die. So 2 times 6 is 12. There were 12 outcomes. So if we're flipping a coin 3 times, what we do with the 3 is we draw 3 blanks. A blank for the first flip, a blank for the second flip, and a blank for the third flip. So blank, blank, blank. First, second, third. And then we put the number of outcomes in the blank. So how many outcomes are possible on the first flip? 2. How many for the second flip? 2. How many for the third flip? 2. So that would be 2 times 2 times 2, which would be 8 total outcomes. Sometimes the wording of the problem says how many different outcomes. We're always talking about different outcomes. Whether they say different or not, don't let that word confuse you. We wouldn't say how many of the same outcome are there. That question doesn't make any sense. So anytime they say how many outcomes, they're talking about how many different outcomes. You will see a lot of problems that talk about license plates. So let's say that we have a 5-character, thank you, that's a good word. 5-character license plate. I feel like that's spelled wrong. License? Is there supposed to have another C? C? C-E. I just switched my C and my S. And it's going to have 3 letters and 2 digits. Sometimes it'll say numbers, but when they're talking about numbers in a number, we're talking about digits, and the digits are the keys on your calculator. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are the digits, and there's 10 of them because we're counting from 0 all the way to 9. And then when you see this, they need to tell you either you can repeat letters or you can't repeat letters. Or you can repeat numbers or you can't repeat the numbers. So we're going to say there's no repetition. If there's no repetition, then if I put A in the first slot, I can't use A again. So we have this 5-character license plate. The first 3 are going to be letters, the next 2 are going to be digits, and there's no repetition. So I have 5 things I have to choose, so I would put 5 blanks. It doesn't actually matter where the letters and the numbers are going to go. It's going to be the same answer. So I'm just going to do the letters first and then the digits. So how many letters do I have to choose from for that first blank? How many letters are in the alphabet? 26. Now you'll see sometimes they'll say you're not allowed to use a certain letter. Like sometimes they say you can't use O because it looks like a 0. And they want to be able to tell the difference on the license plate. If you're reading a license plate, they want to know if it's an O or a 0. So sometimes they throw things out. But as far as we know, we're allowed to use all of them. So we're going to say 26. Once we put one there, we can't use that letter again. So now we only have 25 to choose from for the second one. And then for the third one, we have 24. So these are our letters. And then over here is the numbers. Well, we're saying we can use any digit, so it's 0 to 9. Right, because then it wouldn't be a digit. Okay, so we have 10 digits to choose from. So we have 10 options for the first one, but once we've put one there, we can't use it again, so then we only have 9. Read the problems carefully because sometimes you can repeat and sometimes you can't. So you just have to be sure you read carefully. Okay, you guys have your calculator, so when someone has that, will you read it? 1,000,000. Even? 1,404,000? Is that what you got? Oh. That's a lot of ways. Okay, so that's our first 2. Now we're ready for the next 2 boxes. And our next 2 boxes, we're going to do permutations and combinations because those 2 are also about finding out how many ways there are. So I'm going to make this one permutations. And the one on the right, combinations. And we know our calculator will do these for us, but it's also good for us to know what the setup looks like. So if we have NPR, that would be n factorial over n minus r factorial. And for combinations, it would be NCR, which would be n factorial over r factorial times n minus r factorial. What button do you hit on your calculator to get to where it will do this for us? The math button. So it might be a good idea to write down. You use the math button and then you arrow over to what? Probability. And then you select it from there. Permutations. That's the one.
Miss Tal,
Yes.
If we use our calculator for either of these types of problems, do we still need to write down the formula?
You don't have to write down the formula, but you do need to write down like NPR. Yes. Or NCR and write it and fill it in with what you're plugging in so I know. So permutations, that's where the order matters. We say order matters, but we're also looking at, is each thing different? Is being president different than being vice president? Is sitting in the seat on the right different than sitting in the seat on the left? Is me giving a gift to you different than you giving a gift to me? Yes. Is me shaking your hand different than you shaking my hand? No. So remember, handshakes, that's something that would be a combination. Combinations are when we choose as a group. So if I go to the grocery store and I get to pick out 3 kinds of ice cream, all 3 kinds of ice cream get to come home with me. So that's a combination. If I'm choosing which ice cream I eat on Monday and which one I eat on Tuesday and which one I eat on Wednesday, then that's a permutation because each one is getting its own day versus, let's be honest, I would really just eat all of them the same night, so it doesn't really matter. But eating them all of them the same night, that would be a combination. Okay, it's worth noting that permutations kind of overlap with the counting principle. So sometimes when you see those, you might think, is it a permutation or is it the counting principle? They kind of overlap. There are problems that you can work as one or the other and you'll get the same answer. So let's say we are, let's see, a permutation. Okay, so let's say that we have, just lost it again. Let's say that we have 10 people running a race, and we want to know how many ways they can finish first, second, and third. So we have a race, we have 10 runners, and we're going to award first, second, and third place. Remember that n is always your total number, so n is going to be your bigger number. We have 10 people, so it's 10. It's a permutation because first is different than second is different than third. And how many awards are we giving? 3, so it's 10p3. For the sake of your notes, let's at least write how this would work out. We would do 10 factorial over, and then 10 minus 3 factorial, which would be 10 factorial over 7 factorial. And remember the shortcut, 10 times 9 times 8 times 7 factorial over 7 factorial. I can only cancel factorials when they're identical, and since those are the 7 and the 7, I can cancel those 7s, and I get 10 times 9 times 8, which is 720. So 720 different outcomes for first, second, and third place. Do you see how we ended up just doing 10 times 9 times 8? So when you're you remember how I said there's overlap with the counting principle? How many how many runners are there to choose from for first place? 10. 10 total. And then once that person gets first, how many choices are there for second place? 9. And then for third place, 8. So it kind of overlaps there with the counting principle. You could use either one of those. Another one is, remember that anytime you're organizing all of the items, like if you've got 5 books on a shelf and you're going to organize how many ways can I arrange all 5 books on the shelf? It's just going to be that number factorial. So if you have space and you want to add one more, how many ways can we organize 5 books? Or I could say, how many ways could we arrange 5 books? That would be 5 factorial. So 5 times 4 times 3 times 2 times 1. 120 ways. When we say ways or when we say outcomes, we're talking about the same thing. Ways, outcomes, possibilities, those are all the same. Then combinations, that's anytime we're choosing the items as a group. So if everybody's going to get on the elevator, or I tell you you can pick 3 colors to do your notes with, all of those things, all of the things are getting to do the same thing. If we're choosing people to do group work with, and you're all doing the same work, you're all being part of the group, you're going to be part of a committee. All of those are combinations. So let's say I have 8 books, and I'm going to choose 2 to take on my vacation. Both of these books are going on the vacation. So that's what makes it a combination. I have 8 total books. 2 of them are going, so 8C2. So we remember from the lovely song what our formula is. It is n factorial over r factorial times n minus r factorial. It's a lovely song, it really is. And then you can work that out or you can plug it in on your calculator. Sometimes I think it's actually just easier to write it out. The 6 factorials cancel. The 2 goes into the 8. 4 times 7 is 28. So there's 28 ways for me to choose 2 books if I have 8 books to choose from. Okay, all 4 of those sections that you just did, these 4, are all about how many different outcomes there are, how many ways something can happen. None of them actually asked what is the probability of, right? These were all just how many outcomes are possible. The second half of the sheet we're going to use for what's the probability. And we had 2 different scenarios. We had what's the probability of A or B happening, and then we had what's the probability of A and then B happening. Those were our 2 different situations. So we're going to start out with the ORs. And the OR questions had 2 different ways that they could be. They could either be mutually exclusive, or they could be what we call overlapping. Sorry?
Why did you put the 4?
The or is the main thing. So when you're reading the problem, if it says, what's the probability that I choose Dr. Pepper or lemonade, then you know that it's an or kind of question. If it says, what's the probability I choose Dr. Pepper and then lemonade, that would be an and question. We'll get to those next. So mutually exclusive, remember, means that there's nothing they have in common. So if I say, what's the probability of milk chocolate or dark chocolate? We're not going to have ones that are both. What's the probability I draw a red marble or a blue marble? I don't have any that are both. We're going to use a deck of cards. That will make our problems involve a little less writing. So I'm going to say, for mutually exclusive, if you're doing the probability of A or B, we had this kind of little, you can call it a formula if you want, the probability of A plus the probability of B. So you just found each probability and you added them together. So let's say I wanted to know the probability, if I draw a card out of a deck of cards, what's the probability that it is a heart or a club? So I know by looking at the deck that there aren't aren't any cards that are both a heart and a club. It has to be one or the other, so it's mutually exclusive. I'm going to find the probability of drawing a heart, and I'm going to add that to the probability of it being a club. Up on the board, I have a lovely poster that shows you the deck of cards if you're not familiar or if you need a little bit of help. How many of the cards are hearts? 13. How many cards are there total? 52. This is going to be one of the times I tell you not to simplify yet. When you're adding, you want your denominators to be the same. So it's best to wait until you're at the end of the problem to do any adding or to do any simplifying. Then the probability of getting a club, well, there's also 13 clubs out of 52. And then when I have a common denominator, so I can add my numerators, 26 out of 52, which simplifies to 1/2. But on the adding, we wait to simplify until the end. I'm going to use another cards example for the overlapping. But I want you to remember with the overlapping, we're still talking A or B. But to find that probability, you're going to do the probability of A plus the probability of B. But because there's overlap, there's certain cards you've counted twice. So we're going to subtract the probability of both. So something that is both the first thing and the second thing. We did problems like a peach or fresh. Well, some of the peaches were fresh, so those would be the both. For this, we're going to say the probability of a heart or a face card. So the face cards are all of the cards that actually have faces on them. They're named for people. So that would be the jack, the queen, and the king. And each suit has a jack, a queen, and a king. So if there's 4 suits, that means there's 12 face cards. So we'll start with the probability of a heart. We're going to add the probability of a face. And then we're going to subtract the probability that it's a heart with a face. That it's both. We'll start with the probability of it being a heart. We already said in the last problem there's 13 hearts. So that would be 13 out of 52. Plus, and then face cards, 3 face cards, 4 suits, that makes 12 total face cards. Minus, and then how many of the face cards are hearts? 3. The jack of hearts, the queen of hearts, and the king of hearts. So we're going to subtract off that 3 out of 52. Remember, with adding and subtracting, you work left to right. So you're going to do 13 plus 12 is 25, minus 3 is 22. 22 out of 52. We can simplify that to 11 out of 26. I know on some of the worksheets they gave you decimals as answers also. I don't need the decimal. The fraction is plenty. I just leave it as fractions. All right, so those are our situations when the problem says or. And when it says or, only one action is actually happening, okay? So if I'm drawing a name out of my sticks, what's the probability that the name has an A or an E in it? Probably pretty high. But I'm only drawing one actual stick. Okay. On the and problems, you're doing multiple things. So you might pull 2 marbles out of the bag, or you might wear 2 different shirts, or whatever, but multiple actions. When we're dealing with the and problems, we have and problems that are independent. When they're independent, the first thing doesn't affect the second thing. The first coin flip doesn't affect the second coin flip. Those are independent of each other. And then we also have the and ones that are dependent. In the dependent problems, you often see the word not replaced. Independent would be if something is replaced. So if the item is replaced, they have to tell you that. I'm going to say that again. If the item is replaced, they have to tell you that. So this has to say replaced. If the item is not replaced, sometimes it will say that, but lots of times it doesn't, and it doesn't have to. It's kind of common understanding that if you're pulling two things out of a bag, you're not pulling one thing out and then putting it back in and then pulling another thing out of the bag. You would pull out the first thing and hold on to it and then pull out the second thing. So that's why not replaced, they don't have to tell you that. If the item is replaced, they do have to tell you that. So we're going to use marbles for our examples here. We're going to say we have 2 red, 3 green, and 1 yellow. We're going to use the same for the dependent one. 2 red, 3 green, and 1 yellow. For both of these problems, I'm going to reach in and draw 2 marbles. Remember, even if I just say I draw 2 marbles, you have to imagine I'm drawing them one at a time in order to calculate probability. So we're going to say, what's the probability that I draw a red and then a green? And I'm going to say with replacement. With replacement. So once I draw that red, I put it back in the bag, shake it up, and then I draw another one. The way that we do these is with multiplication. So we're going to do the probability of red times the probability of green. Probability of red, well, how many marbles do we have? 6. The number one mistake that gets made is people count the wrong total number. So how many times should you count the total number? At least twice. Double check your counting. So 2 plus 3 is 5, plus 1 is 6. 2 plus 3 plus 1, 6. Okay, so the probability of getting a red is 2 out of 6 times the probability of getting a green is 3 out of 6. I'm going to be picky on this test. I don't do this a lot, but you must simplify before you multiply. I really want you in the practice of simplifying before you multiply, so if you don't, I'm going to take off a point. I don't want you just multiplying and getting huge numbers. So simplify first. What simplifies? Well, yeah, the 2 and the 6. Now look, I have a 3 here. I can either cancel the 3 with that 3, I can cancel diagonally, remember, or I can just simplify the 3/6 to be 1/2. It doesn't matter. I'm going to cancel it with just the 3 just so you can see how that works. And then everything is as simplified as it's going to get. So 1 times 1 is 1, 1 times 6 is 6. So the probability that I draw I draw red, then I put it back, and then I draw green is 1/6. Okay, dependent, we're going to do a probability. We're going to do the same thing, red and then green. But this time, we're not going to replace it. When we do these, we do the probability of red and then the probability of green after red. We do the probability of red times the probability of green after red. On these, you have to assume that you got what you were looking for. So on that first, in order to calculate green after red, we have to assume that we're holding a red marble outside the bag. Okay. So the probability of a red is still 2 out of 6. But we had red, green, 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 yellow. And now we are holding that red marble. So now that we're holding it, we still have 3 green marbles, but how many total marbles do we have? 5. So it would be times 3 out of 5. We're still going to simplify before we multiply. So the 2 6 simplifies to 1/3. We're going to simplify those 3's again to 1 and 1. Now we're left with 1 times 1 on the top and 1 times 5 on the bottom. So the probability is 1/5. Which one of those is more likely, for it to happen with replacement or for it to happen without replacement? Without replacement, because 1/5 is bigger. And the higher the probability, the more likely something is to occur. What's the probability of something that cannot occur? 0. What's the probability I choose a student in this room out of a hat and they're 16 years old? 0, because none of you are 16. Okay. What's the probability that I choose a student out of this classroom and they're in the 8th grade? 1 or 100%, because everybody is. All right, so 1 means something is definitely going to happen. 0 means it's never going to happen. All right, so now what you're going to work on is you're going to go to the tab that says assignments, and you're going to work on all of these quizzes. And then when you're finished, if you have time, you can work on the probability review that's the last tab in the packet.